Hello, everyone. My name is Paul Lancaster, and I'm with Red Hat. We were able to sponsor this event, and much thanks to my former college roommate, Todd Rapone. He's somewhere around here. He was on the panel this morning. But we wanted to talk a little bit about how Red Hat looks at open source, and specifically how, in particular, the open source vLLM project, which is actually a part of UC Berkeley, has come to be very much synonymous with Red Hat due to an acquisition that we made earlier this year of a company called Neural Magic. So I've asked Nick Hill to join us and to give a bit of a talk about vLLM and why folks should be considering using vLLM and what vLLM is about. And with that, I'll turn it over to Nick. Thanks, Nick.
Thanks, Paul. Hi, everyone. I'm Nick Hill. I work for Red Hat as part of the AI engineering. In particular, I work on sort of scaling the inference platform for serving large language models. And for the last couple of years, my main focus has been on sort of furthering the vLLM open source project, which I'm going to give a bit of an introduction to, some of the technology behind it, and then how we've been sort of working successfully between UC Berkeley, who started the project, and industry. The goal of vLLM is to build the fastest and easiest to use open source inference engine. That's kind of the thing that we're all focused on. What's an LLM? I think probably most people have heard of it by now. Some of you may know this, but I'll give a little recap on how LLMs actually work under the covers. So you probably, when you use ChatGPT or one of these other services, you give it some text as input, and then it starts to respond with additional text. So the first thing that happens, the text gets sliced up into what are called tokens. So there's like a big fixed vocabulary. For a lot of the new models, it's quite large, 128K tokens for Llama models, for example. And then, so each of these has an index. So that's kind of the first thing that happens. And then the LLM works with this sequence of tokens from 0 to 128,000. And basically, the LLM is just a function that takes this sequence of tokens and decides what the next token is going to be, predicts what's most likely, given all the ones before. So to generate text, you just reply this repeatedly with all the tokens that have been generated, and you pass it all the tokens, including the next one, etc. Problem with this is it's very slow. It's inherently sort of sequential. And then the amount of computation just to generate this one next token is quite large. So if with these, now the sort of reasoning use cases, or things like that, there's very large amounts of text that you could be generating. So it takes a very long time. It has to run on very expensive hardware. Part of the reason for this is that the key part of how it computes the next token is using this attention mechanism, which you've probably heard. That involves doing computation between each token and then all of the other tokens that precede it. So as the tokens increase, this is sort of order n squared complexity, and this is each new token it's adding. So that's the first problem. So yeah, like I said, performance is critical. We want to kind of maximize the throughput because that's basically what the cost is based on. So the first thing we can do is see that, like, between each token that's generated, the sequence that's being used is actually mostly common apart from the very last one. And there's a lot of redundant computation that was done in sort of intermediate states that we can reuse from like the first token to the second token. So if you see here, the green represents like what was done to generate the last token. We had to compute the attention between all of these different tokens. The only new sort of intermediate states that we have to generate, these are the sort of key and value matrices, they're called in the extension operation, are the ones that are with the next token that we chose from the last iteration, that's easiest in this case, and then all of the others. So you can see each time it's only a function now of the length of the sequence so far, not like a quadratic function of that. So this doing this optimization when we store the states from the last one and use them in the subsequent computations, it sort of takes it from quadratic to linear. So that's like a sort of key component of vLLM and all of these other inference frameworks. The problem with this, though, a new problem, is that these intermediate values that are computed are very large, and so that's the next thing we have to contend with. So KB, using this KB caching technique, accelerates how fast you can generate each next token, but there's still a bottleneck because you have to copy all of the model weights to the GPU compute for every token you generate, and the models are very large, sort of billions of parameters, which can be tens of gigabytes that have to be transferred to the GPU memory for every token. And so we need to parallelize. We can batch multiple sequences together. If you're generating, multiple users generating text together, then we can put them in a batch and process them in parallel, and that means we get a sort of bigger, more compute relative to the amount of data movement that we have to do for each token. And then the KB cache now includes the history for all of the sequences in the batch. So you have a batch that we run together. So parallelism is the other main thing we can do to kind of help with the cost and help with the utilization. So in a production setting, you may be running a server where people are sending requests, like to ChatGPT, like you would do ChatGPT API with some application running on top. And these requests are coming in at different times. Like in traditional systems, what you might do is have a queue where you queue up the requests, and then you send them as a batch, like after some period of time. And this can be done, and it helps. It's a good first step. And because the generation of the text takes actually a relatively long time, if you've got lots of requests coming in, you can just queue these up while the others are running, and then use those for the next batch. But the trouble is, like you can kind of see here a bit, requests are actually different. The number of tokens that get generated is different between different requests. The model decides when it wants to finish, like it comes to the end of a sentence or something, so it might give a one-word answer in one case, or it might like generate an essay in another case. And if these are both in the same batch, then you're sort of just waiting for the longest request to finish before you can do any more computation. So this is like actually super inefficient, and one of the sort of innovations wasn't the innovation that started vLLM, which I'll come on to, but this is sort of a key. It works along with it, and it's one of the key ones. It's called continuous batching. So for this, what we do is actually reconfigure the batch between iterations. So as I was explaining, each token generation is effectively independent, so that each time step we're generating the next token for all of the sequences in the batch. If one of them finishes, like if the model generates a special end of sequence token for one of them, we can remove that from the batch, and then we have sort of space in the batch to then add new sequences that have been queued, like between iterations. And so you can see in the sort of lower picture here, this obviously keeps the batch full and helps a lot with the latency, because new requests coming in don't have to wait for all of the existing requests to finish before they can sort of get started and start streaming the tokens as they generate it back. Back to the KB caching. As I was saying, the problem now is that it's these intermediate states are tensors that have to be stored in the GPU memory, and they're very large. It can be up to like megabyte or more per token, and if you've got sort of thousands of tokens, or even up to millions of tokens, or tens of millions for the new Llama models, for example, this quickly fills up the available GPU memory, and so that makes a constraint on your throughput, because you can only store so many sequences at once, especially once they get very long. This can become a limiting factor for the throughput. The KB cache itself is a tensor that's used in sort of matrix multiplication operations for the attention operation. And typically these would be sort of contiguous, so you'd have like your input tensor and then you multiply it with the query tensor that's based on the new token that you've chosen from the last iteration. But these typically have to be contiguous, and after the next iteration you append, the KB cache grows, and you have to append the values from the last iteration. But the trouble is, because you don't know how long the sequence is going to be, you don't know how much memory to allocate for it, right? You're appending to this region of memory each time, and so it's very inefficient if you just allocate the maximum possible like length of sequence, because you don't know. Again, it could be a few words or like a whole essay. So this is essentially fragmentation. This picture here kind of shows the problem. There's different types of fragmentation that happen when you try and reserve space for the KB cache and the GPU memory for all these different sequences. So on the left-hand side, you can see it has the slots for the prompt, which is the sort of input tokens, artificial intelligence is, and then we've appended to the KB cache to generate the next two, which is the future, and that's where it's got up to so far. What's going to happen is we're going to generate 3 more tokens before we get to the end of sequence, so that's like the next 3 that are reserved. But we actually reserved much more because we didn't know how long the sequence was going to last. So that's the other sort of 2040 slots used. And so that's essentially that space was wasted, right? Maybe we were at capacity, we couldn't fit any more sequences in, we'd reserved this for a particular sequence. So that's like a form of fragmentation. Because we didn't know how long the sequence was going to run for. There's also fragmentation just because in the memory we need to allocate these multiple contiguous blocks, so it's just like a standard fragmentation problem. You can see the next request, the gap between the next request, and maybe we've got lots of these gaps that add up to space for a new sequence, but because it's not contiguous, we can't fit it. So there's that kind of fragmentation, and there's also the fragmentation in that we only need to use the if it's a very long sequence we're generating. While we're generating it, we don't actually use the space until we get later in the sequence, if that makes sense. So there's actually sort of unused space, even though we're going to use the space, it's sort of prematurely reserving it. We could, if we had some shorter sequences, we could have used that space, right, to hold the KB cache for those and run those in parallel. So that's like essentially another kind of fragmentation. So the original innovation of vLLM, the project, was something called page detention. And this is essentially allowing you to do the operation on the KB cache to generate the next token on non-contiguous data. So you can, the V in vLLM is sort of stands for virtual, because it's analogous to virtual memory in operating systems. So it has a notion of paging. Instead of pages, they're called blocks, and that's a block is a certain number of tokens in the KB cache. And so what we do is allocate, as the KB cache grows, we don't need to allocate contiguous memory, we just choose the next block, allocate the tokens in a particular block, and then maintain a mapping, this sort of block table, which is like a page table in an operating system, maintain a mapping between the sort of logical KB blocks representing the sequence so far. So you can see for the first request that Alan Turing is a computer scientist and mathematician, so those are logical, but the actual location in memory of those is sort of dispersed in different places. You can see from the physical representation. The key thing in vLLM was these kernels that could work with that contiguous memory, and then a sort of scheduler to manage the memory in different blocks. And so you can see now this sort of solves the fragmentation problem, because you allocate as you go, and all you need is, the most wastage would be sort of some portion of a block, which might be, typically 4 or 16 tokens, something like This is just another picture showing the mapping. So this was the original paper from that came from the UC Berkeley Sky Computing Lab. Woo-Sok and Johan were the sort of primary authors about 2 years ago now, and then it was open sourced as a project vLLM in June 2023. One extra bonus related to this KB caching is that you can also share beforehand, because each sequence would have its own space for the KB cache. You can now share the blocks between different sequences, so you kind of get this deduplication. If you're sending in requests that have the same, they start with the same tokens, which is often the case in LLMs. You have something called a system prompt, which is like a prefix that all the prompts have that kind of tells it how to behave. Because that's common, you don't want to like recompute that between requests. You can save that. You don't need to flush the cache, and we can see, okay, the token's already, is there some prefixes already in the KB cache, and we can reuse that and not have to recompute it. So that's something you kind of get for free, along with this sort of parallel sampling, which is where you send in maybe a long prompt and you want to generate lots of different completions for it to choose like the best response. Instead of having to recompute everything based on the same prompt, that's done once, and then all of those, you share the same intermediate values. So that was like something that came, automatically added to vLLM from the page detention. So today the project's, going from that early sort of PhD project in 2 years, it's now sort of become the de facto. Sorry, the line of some of the pictures is a little bit off, but it's sort of the de facto standard open source server for LLMs. It's all over the place. There's 100,000 people installed it just the first month of the year. It grew 10x in 2024. And it's been, I think the main reason for the success is that they've been, Woo-Sok and Johan were like very open from the outset. There were 1 or 2 other projects at that time that were doing similar things. But they were, under the control of a particular organization. They were, very keen to have people get involved and promoted, like a lot of the early sort of heavy contributors to be committers on the project and sort of share the leadership of the project. And they sort of expressed this commitment to remaining open and, not switching the license like some other projects have done. After they started an open source project. This is the team from UC Berkeley who work on the project. Simon on the left is sort of he's like, does all of the administration and sort of holds everything together, all the kind of community stuff, like he's superstar. Woo-Sok and Johan are the sort of top, the next top 2 on the left there. And then there's Jerry and Jan from the Berkeley faculty on the bottom right who sort of support the project. And then, along with those folks, the committed base has become very diverse. There's a sort of really good split between industry and academia. Obviously the Berkeley folks, but there's other academic institutions contribute. A lot of them are sort of independent students in different parts of the world. And then Red Hat are the sort of biggest commercial organization, I guess, that contributes to the project and the maintainers. But the other sort of key ones that have committers are Anyscale, Hugging Face, Meta are getting more and more involved now, Roblox, Sentinel, and there's a sort of long tail of other committers. And we sort of work almost like as a team that spans these organizations on a daily basis. We're all sort of focused on the same goals of making vLLM succeed as the inference server that everyone's used. This was like I think towards the end of last year, one of the events that we sort of, it's a kind of selection of a lot of the core maintainers of the project. So this is another view showing, how it's the main contributors are sort of split between a bunch of different organizations. There's hundreds of PRs we get every month. long list of organisations that are now sort of committing, reviewing, and getting involved in some way. We actually just passed the 1,000 contributor mark, so that was a big milestone. It's sort of run as a distributed engineering organisation, so I know, the whole topic of this event is open source, but that's sort of, I think we sort of embody that with the way we collaborate. Everything's done through GitHub issues, PRs. We have design docs in Google that everyone sort of works on together. We use Slack all the time, very active Slack discussion forum for support. We have weekly community calls with anyone can join, where there's discussing what everyone's up to, coordinating who's focusing on what, and then we have other calls like for the smaller ones for the leads where we sort of do more of the steering type things, and then discussions as needed. The roadmap is published and quarterly and with input from the community. So there's again a very strong emphasis that the roadmaps just is collected from all the input. It's not like any one agenda of a particular company, and then we sort of figure out the priorities based on who's going to use these features the most. We organise meetups roughly every 2 months. There's been about 10 so far over the last year or two. Most of them in the Bay Area, but now we've started to have them in other parts of the world. Just had one on the East Coast recently that was hosted by Red Hat and Google. There's going to be another one in New York, I think, in the next couple of weeks. And then there was one in Singapore and one in Beijing, also in the last couple of months. And these are typically hosted by one of the sort of selection of the organisations who's hosted the meetups, and we have a project update usually from Berkeley guys or one of the other maintainers, and then speakers from one of the companies usually talking about how they're using vLLM and what the contributions they've made, or like how things they've learned about using it in production. There's some pictures from the meetups. The left one was at Meta a few weeks ago at their headquarters. That was probably a record attendance. Usually they've booked up in capacity, but they let a lot more people into that one, so we had like hundreds of people. We also ran office hours. These were also hosted by Red Hat. Before that was the Neural Magic folks this is a startup that Red Hat acquired that were heavily involved in vLLM, and I'm part of that team now. I didn't belong to Neural Magic. I actually moved from IBM Research into Red Hat, but joined up with the Neural Magic folks. These are every 2 weeks. We sort of usually have a speaker deep dive on a particular feature or something that's being worked on in the project. So there was actually one just like a couple of hours ago, the latest one on, you can see there, on optimization for Google GPUs from a software engineer at Google. So sponsorship's a big part of the project. All of the PRs get tested. There's like a test suite with thousands of tests that run on every PR. This is quite expensive because we need to test on like multiple hardware. It's cross-platform. The GPUs are expensive, so there's a lot of companies sponsor us and help pay for the bills, which I think runs to like $30K a month or more. These are some of the organizations that contribute, so thanks to all of those. We closely collaborate with the model creators, so you guys are probably familiar with a lot of these open source models: Meta, Llama, Mistral, DeepSeek, Databricks, and a lot of the others. And then also with the hardware vendors, we collaborate very closely. Some of them contribute directly to the project. In other cases, we sort of work with them. But that's another major benefit of the LLM over sort of similar solutions from NVIDIA, for example. which are sort of obviously more focused on their hardware. We want to be the choice that people can kind of move between hardware as needed and works well on sort of diverse set of platforms. So yeah, we work closely with NVIDIA and often faster than or competitive with their own sort of inference solutions. AMD, Intel with their Gaudi chips, Google with the TPUs, and Neuron, the Inferentia and Trainium chips from Amazon. These are some of the companies that use vLLM and other projects that build on it. We think the open, like as I was saying, the open governance and the open sort of architecture are key to the success of the project, and why it's really taken off. The community is. I've been involved in other open source projects before, and this is seems pretty unique in the sort of the community part of it. A lot of that's down to Simon and others like that sort of organise all these things. We want it to be easily extendable, so it's sort of modular, and have it easy to be modified. A lot of companies actually have their own private forks of vLLM. A problem that they've had historically is that because it's changing so fast, it's very hard to keep a fork consistent with like the upstream project. That's something that more recently we've been trying to kind of stabilize things and make them more modular. We learnt a lot of lessons from the first sort of year or two of development, where a lot of things were bolted on and it grew in a sort of organic way. And we've recently had this sort of what we call a V1 re-architecture of the project, where we sort of rethought a lot of the core pieces and designed them from the ground up, incorporating the lessons learned and better sort of integrating the different optimizations instead of having them sort of bolted on. So as part of that, the modularity is helpful then for companies, like I say, that have their own forks and want to build their own use cases on top of vLLM. At the beginning, it sort of started partially as a platform for other researchers to build, to do other research and implement their ideas, and that's still a very big part of it. There's a lot of, there's papers coming out every week with new sort of ideas for inference optimizations or features, and vLLM is sort of the default platform typically people use to try these things out, or if they're comparing it with other solutions, it's always against vLLM. So that's sort of, the key things in the community. It's part of the Linux Foundation, and more recently joined as a sort of PyTorch ecosystem project. So again, sort of the sort of commitment to the open governance is part of that. What does it do? I guess backing up a little bit, I talked through some of the motivating technology and the page attention innovation. But since then, it's sort of grown into a fully fledged inference server, and the support has sort of broadened for lots of different things. So I'll run through some of those. So it's actually just a Python library, is one way of using it. So you can do sort of offline inference. You can just import vLLM, or you put this LLM interface, and you can provide the name of a model from Hugging Face, and it will load the model. And then you can just give it some prompts and call the generate function, and it will run everything behind the scenes in an optimal way to output. So it's easy to integrate and play with in notebooks and things like that. The other way of using it is as a server for online servings. This is where, so I talked about before, you may have lots of requests hitting it, and this is where the continuous batching comes into play and that kind of thing. So you can just run vLLM serve. We publish Docker images that typically people use to deploy this, and then it exposes a standard API which is sort of compatible with the OpenAI APIs that they use. If you use these services, that's the one that most people kind of conform to. So if you have something that works with against OpenAI, then you can switch it out and use it with vLLM and vice versa. We support a whole range of different classes of models. So there's often a scramble, when we have relationships, as I mentioned, with the sort of key open source model factories, and we kind of often get advanced warning of like a model that's coming and work with them closely to make sure it's supported well on day one. And so we have support for all the kind of most popular, the latest models. Llama 4 isn't mentioned here. That was probably the newest one. They're like, dense transformer models. A mixture of expert models are sort of become more and more prominent now, especially with DeepSeek. You guys probably heard about DeepSeek. That's has this MOE architecture, which is where different parts of the model, it's sort of like the weights are split into different experts that are trained independently, and then there's a router that combines the experts to get better results without having to load all of the weights for every token. There's some unique optimizations and architecture considerations for deploying these kinds of models, especially when you have a very large number of experts and you want to do it in a distributed way. So that's been a big focus lately, and that's a big part of the support in vLLM. Multimodal models, so you can use it with a lot of the new models. You can pass in images and write questions about images and include that, and that's also part of the OpenAI API. So that's a big part of support. There's a couple of folks, Roger from Roblox, who's on one of the committers, and Cyrus, who's a student, a PhD student in Singapore, is sort of the lead on the multimodal stuff. I think, we're sort of probably the best open source model if you're doing multimodal as well. There's these sort of emerging architectures, the state-space models like Mamba and Jamba, embedding models that can be used for things like classification and in conjunction with like RAG type use cases where you're creating encodings for text instead of generating text, and then reward models which are used for post-training type workflows. So RLHF and things like this, like fine-tuning models, you have to have an inference as part of that process, and so we work with a lot of those frameworks for doing this reward modeling as part of the post-training. I think I already talked about the diverse hardware support. PyTorch is a big part of vLLM. It's sort of the core. They describe it as like a narrow waist. So that's the abstraction where most of the hardware implements, PyTorch integration with Torch compile and things like that. So most of the higher layer of vLLM is built on top of PyTorch, and then there is a lot of custom parts for different hardware, but mostly it's through PyTorch. And then there's like many other optimizations which I can talk more about if anyone's interested in anything in particular. But things like model compression, so neural magic, that was a big part of their history, was looking at how you can compress models to make the inference more efficient. So another way, I was talking about how important the KV cache is and the fact that becomes a limiting factor. That's you can use lower precision, like 8-bit representations for the numbers, or even 4-bit instead of the typical 16-bit. And there's ways of doing that. There's techniques to do that which minimize how much accuracy you lose, because you think if you reduce the precision, it's going to make the output worse. But quantization, if done the right way, there's a lot of redundancy actually in the weights of these things, and if done the right way, you can get the best of both worlds and use like half the space, so you effectively double the amount of KV cache you can have. It's a lot faster because the amount of data you've got to move to the GPU is halved, or split by 4. So that's a big part of what's the optimizations of vLLM. Distributed inferencing, for like very large models, there's different ways that you can split them up across multiple GPUs, like they might not all fit on a single GPU. And there's other reasons why you might want to speed things up by parallelizing across multiple GPUs. So these are all different ways you can slice up the model and perform the same operations in a distributed way. Tensor parallelism is sort of where you split each layer of the model, and pipeline parallelism is where you put different layers on different GPUs. Data parallelism, you have a copy of the model on different GPUs, and you just send, you split your data up. And then expert parallelism is where, for these mixture of expert models, you put some experts on, you sort of distribute the experts amongst the GPUs, and then that can sort of help with the reduce the overhead of the weights that you're having to store. Let's see, chunk prefill scheduling is where typically when you're computing the key values for the input prompt, you have to do that once for the input prompt, and then subsequently you just use those saved tensors along with the next tensor to generate the next one. With continuous batching, that's a problem, because if you have new requests come in, you've got to then recompute their KV cache, and then everything else is kind of held up while you do that. Chunk prefill is where you can sort of split up that first computation of the input prompt. That's more intensive because you don't have the cached values for that. And you can actually combine it in the same forward passes of the model with like the decode phase, which is where you're generating the next token. So that was like something that was, didn't exist when vLLM started, but was incorporated, and now it's like the default behavior in the new version. Prefix caching I explained a bit about, but we've now made that automatic. So if new tokens come in and there's already KV cache for some of the prefix of those tokens, you just benefit from it automatically. Speculative decoding is another technique which is quite clever, where you can use a much smaller model or other techniques that are much cheaper to predict so many tokens ahead, and then you can batch those tokens in one. So you're sort of converting something sequential to something parallel by doing sort of prediction. And often text is very easy to predict. So like there's an obvious next, some sentences, the obvious next word will always be and or something, right? But the cost, you may have a very large language model, which it's going to cost you just as much to generate that and as it is to generate some other token that might be more complicated. And so speculative decoding, you use a smaller model to much more quickly predict a few ahead, and then the large one can actually verify them all in one go in a single iteration, and that actually can speed things up a lot. There's a whole bunch of variations of that technique. So a challenge is to build sort of modularity such that we can support all these different variations, and as new ones come in, they can benefit from the same sort of underlying framework. Multi-LoRa, maybe I'll skip over that because I would have to explain a bit more about the LoRa adapters, but you can basically have multiple, you can train sort of models, adjunct models on a base model for a particular task, and then have a lot of these different tasks share the same base model and actually share the same invocation. So different requests can have basically their own version of the weight, modified version of the weight as they pass through the model for different tasks. So that's another that was something early added to vLLM. And then structured output is sort of constraining the model. So each step when you're generating a new token, the LLM actually generates a probability distribution over all of the whole vocabulary. So it doesn't, the model doesn't actually tell you what the next token should be. It just says, it's just like a prediction, like most likely next token will be, based on probabilities, right, for like across the whole 128,000. So that might be very flat, where there's a lot of tokens that are equally likely, or in the case where it's like there's an obvious text token like and or the or something, right, you'd have a big spike. So there's a stage after the model produces this called sampling, where you can either take the most likely one, or if you want some more creative output or something like that, you can like use some other algorithm to choose, like pick randomly from the top, 10% of the probability mass or something like that, or pick randomly from the top 10 like tokens, most likely tokens. Structured output is like one of the other filters you can add, where you say, okay, I want my output to conform to some schema, like JSON or something like that, right? And so what you do when you have these probabilities is you mask out all of the tokens that aren't, that based on the schema, what the next text that might be allowed at that, given the preceding text. And at each step, you mask out all the tokens that are not allowed from the ones that are output from the model, and then you just have the probabilities that remain for the allowed tokens. And so based on that, you can sort of you steer the model to output in a particular, with particular constraints, but it's still the model choosing within those constraints. And so if you say, I want to make sure it outputs JSON, if you've used OpenAI or some of these, they have like a JSON mode. The models now are very good that you can ask them, please output JSON, and it will mostly be JSON. But using things like this, you can further constrain it so that it's like impossible for them to not produce JSON, essentially. Okay, and then, apologies, there's some nice animation here, but I had to convert to PDF, so lost that. But it's just to say that a lot of these things I just described, they kind of work together synergistically. They're sort of additive, so you can see, like, put it all together, you can increase the performance by sort of orders of magnitude without, if you hadn't had these optimizations. So I think that's it. All I had to talk about. I guess I've got 10 minutes or so left for questions, if anyone has any. Thanks for listening.
Well, thank you so much. And I guess if no one has a question, we have about, 10 minutes until our next session. You have a question. Great.
All right.
So you mentioned that it supports all the LLMs that conform to the OpenAI specifications that has the prompt in the JSON format. Are there plans, or is there support also for models that just answer with text, like Google Gemini is just text, doesn't have the JSON format for system prompt, user prompt, system prompt, and so on?
So actually, all of the models, the sort of base layer is raw text for all of the models. Some of the models, like when you have chat models, they're trained, those get fine-tuned on a particular kind of schema for, like you said, you have it should be formatted, the conversation so far should be formatted in a particular way. But that's, that within vLLM, that's basically, it's all below that layer. So it's just text, right? And it's the model that understands that. We do have, like, as part of the API layer, a sort of templating. So different models have different formats for how this conversation gets structured with special tokens and delimiters and things. And so you can sort of plug in for a given model, like Llama or Mistral and things like that. You can plug in sort of custom logic so that it will know how to format for that model. So when you're running that model, you can pass it more like something more structured to say, okay, these are the conversation terms, and then it will format the text, but at that point it just gets tokenized into, it's just some text that turns into tokens, and the model works the same way regardless. The tool calling, I actually forgot to mention that as one of the features, but that's another big thing now with the chat models, right? They can be trained to sort of understand what tools they have available to use, and then output, say, okay, I want to make a call to some outside service, or I want you to run this command. That there's integration with that. Again, this is all sort of in the top layer because it all ultimately just gets excuse me, converted to text and then to tokens. So the sort of core engine is just works on these tokens from a vocabulary. At the end of the day, that's all it works with, and it just gets converted to and from other sort of templates and formats. And the structured output thing I was mentioning, that's more for the output rather than the input, and it's saying that actually can get used in conjunction with some of the tool calling and the chat stuff just to make sure the model conforms to what you're expecting. So yeah, again, those things all kind of work together. That answers the question. Thanks. Good question.
So I have a question on the dynamics of how development happens and how decisions get made and things like that. You had a really cool slide where you mentioned you have this like open roadmap and you have people that discuss it as a group. And I think you mentioned something sort of in passing, like, and if there are like disagreements, then we kind of like work it out and we align on a roadmap. And I feel like that sentence was doing a lot of heavy lifting. And so I'm curious, this is with my Jupyter hat on, like one of the hardest things to do is to just get a bunch of people to agree on A, what they want to do, and then B, to like have the discipline to only do that thing and not like all of the other things that they want to do. And so I'm wondering what that looks like in practice in the vLLM world, like what infrastructure, be that like social infrastructure or like process infrastructure or like decision-making infrastructure you use to make that be like a tractable problem that doesn't just like burn everybody out all the time?
That's really good question. The truth is, like, we have had very little process. Like, it's been a sort of quite ad hoc in the way we've gone about this, and often it seems to have worked out. I mean, one of the problems, as I kind of alluded to, is we were doing too much, and I mean, it's still partially a problem. We don't want to sort of say no to people, especially if they're willing to contribute things. And so it's that's been sort of like a blessing and a curse in terms of, we have a lot of features, and we're very open to adding new things. But then it can cause a lot of technical debt, and then things don't work together and stuff like that. So there has to be some decision making. So we sort of try and walk that balance. Like we're biased towards sort of allowing things, but we've become stricter in terms of the the quality bars before things can go in. I mean, in this space, I guess again different to other open source projects I've worked on where there might be some feature that's added, and then you sort of iterate on a PR for like months to get it perfect. Because like AI is moving so fast, there's just the culture is a lot more like we just need to get in and move on to the next thing, and then it's going to change anyway. I guess it's more more accepting of new things, we just have to then deal with the refactor and deal with the problems, right? We just release very frequently. Sometimes there's an issue, there's bugs, right? We just release again the next week. There is decision, for large things where someone may have opened a PR and it sort of doesn't fit. It's sort of incompatible with the direction that we, decided. Then, there'll be some discussion, and there are points where the maintainers sort of make a decision and say, look, we can't take this because we're going to go in a different direction. But yeah, it's not there's no sort of easy solution, I guess, there. Does that answer the question?
Yeah, and I guess I'm curious, like, what if someone says, I think we should do X, and somebody else says, actually, no, I think we should do Y, and those people are both maintainers, what happens next? Like, how does that tension get resolved? I don't think, I'm not sure we've had, I don't think there's been any sort of like strong, because most of the things we want to do are sort of in the general interest. Everyone's trying to do the same thing with these things. Like when a new model comes, like DeepSeek, it sort of blows everything out of the water. So like all the companies that are involved are going to want the best. I mean, that's going to be a priority for everyone, right? So that it's sort of like
there isn't many things that are specific to a particular company that aren't sort of the top things for everyone, right? Like there isn't too many of those. So I don't know, we haven't had many of those like hard disagreements that I can think of yet. And maybe it's to do with the, just we get along very, the maintainers as a team, like we've been sort of working together for a long time now, and everyone sort of knows each other well, and it feels like it's we are a sort of team ourselves versus like, just representing a particular other organization. So, yeah. Thanks.
Any other questions? No? Okay. Let's give Nick a last round of applause.